Okay, welcome to the September 16th Propeller 2 Live Forum. Today we'll have a couple of presentations on the Babel board and floating point debug, a little more in detail. Today we'll have those two presentations and then open discussion. Next week, on the 23rd, we have the P2 arcade machine presentation from Graham. And Thursday, September 30, we will have a presentation from Michael on the new board coming with extra RAM 32. Is that 32 megabytes, megabytes of RAM?
32 meg.
Good. So we have a request from Bob from the forum. He has a Hello Propeller 2P2 examples. If you're a forum member, you probably saw that doc. He's been working on it and improving, and he's asking for feedback from the forum. If you go to the forum thread, if you check that doc, he released a new version. Today he couldn't join us, so he asked me to request for feedback. You can go to the forum, take a look at the doc, and provide any feedback there. Also, one of the reasons we had to reschedule Michael's presentation is that he's out, he's traveling right now. And we have Jeff, as you saw in the recent presentation, working hard on documentation. So the people that usually are roaming the forum for supporting Parallax customers trying to get those propeller chips going, is one is in vacation and the other is kind of deep in a project. So any of you that feel, you can give a hand over there in the forum, we can use your help there. Just make sure that anybody getting started with the propeller can keep going. And eventually Jeff or even Michael can get there, but to add anything extra, or if it's a little more complicated. And with that being said, we are good for Lachlan with the Babel board presentation. Are you good to go? I stop share?
Yeah, I think I'm right, Ari, thank you. Yeah. So this will be a quick presentation. It's just, this is a small circuit board we've been making and using, which breaks out the P2 accessory headers to half a dozen useful form factors. So there's just a couple of headers there which plug onto the P2 eval board. Should also work with the other smaller, like Johnny Mac breakouts and things. And what we found is there's a number of peripheral boards which are available from Microelectronica or the Digilink P-mod modules, which are popular with FPGAs. And all this does is rewire those 16 I/O pins to a variety of useful formats. So I'll just run through what those formats are. Share the screen. Sorry, just positioning things so I can see what's going on. Okay, so so we've got 7 different modes which this can be used at, and it just involves just soldering headers in different locations, depending on which configuration is useful for a particular application. The first one, we've been using these small LCD screens. Brian's been writing some drivers for these and other small displays. There's some kind of commonality in that they have 8 pins. And that's where the commonality really ends. So you can kind of put different functions on different pins. Of course, the P2 can kind of rearrange functions according to where the data and clock pins are located. Yeah, so the first kind of mode, I guess, for this breakout board is to accommodate to these small displays, OLED and LCD displays, which are becoming quite cheap and readily available. The second mode is accommodates an Arduino header, at least the side where all the I/O is, and so The Arduino shield would go mount on the top of those, and pins D0 up to D13, as well as the I2C pins are connected across to Propeller's P0 through to P15. You've just got a couple of connections remaining from the
we just lost Lachlan. The presentation is still going, but let me see. He's still there. It shows that he's still there.
Looks like some major buffering must be going on.
Let me see if we cannot get him back. Now he is gone.
He'll probably pop back in. Yeah, he's not even.
Yeah, let's wait for a second so he can just join back in. Otherwise, we'll go to the next. We wait for a second and I don't see anything in chat. So Chip, are you ready just in case to get to the floating point?
Yep. Yep.
Oh, okay. So I got a text message from Lachlan and power out in. Yeah, he lost power, so he's out.
Oh,
We will resume with the presentation next time. So we will go then ahead with the floating point debug update from Chip, and I'm going to stop sharing the screen so you can jump in.
All right, let's see here. I'll share my screen. There we go. Okay. Can you guys see this?
Yep.
Okay, little program here. So what I do here is, here's the FDEC, right? That lets us print decimal. So we can see what the value actually is in raw binary or hex. And I initially assign it about the biggest number that can fit. 3.4 times 10 to the 38th would be like the highest. So I put 3 in, just a nice even number. And then I keep dividing it by 10. And after like 85 iterations, it goes all the way to 0. We can watch the decay. So when I do a Control F10 to run this, starts out up here. Let's see here. There you go. You can see initially on this first line, we have the full value. And then as we divide it by 10, the exponent keeps dropping. We can see the floating format over here kind of changing as we go. And then when we get down near the bottom, let's see, our number holds. And then see, when we get down to about, I think this point right here, this 0020, our exponent is now 0. So we're dealing with now denormalized mantisses that now just keep dividing by 10 until gone. 02 is the last thing. We divide that by 10 and we get 0. And then we're just terminally at 0 thereafter. So we can go down to like something times 10 to the minus 45th. And you can see here sometimes, we have a nice even 3 point, all zeros, and then sometimes we get a 1, sometimes we get a 2 point. Actually, the 2.99 never occurred until we started having our, our mantissa denormalized deteriorate. So it just didn't have the resolution to hold the value anymore with all those trailing digits. So anyway, that kind of shows that the whole thing works. The code for it didn't really, it's a real pigsty right now. I got to tidy it all up, but the code wasn't really that big. The pain was that I had to do a lot of floating point multiplies in order to keep things, you know, in workable ranges. So here's a table here that, you know, shows all the exponent values, powers of 10 that we use. So if we have like a super huge number, we'll wind up multiplying it by this super small number in order to get, you know, 7 significant digits out of there. And then we multiply by this huge number if we had a very small number. Because the point is, ultimately, we have to convert and do a round operation in order to get 7 significant digits, if that's what we're after. So here's the floating point multiply. I couldn't use the Cordic, you know, because on a debug interrupt, we don't know if the customer code is using the Cordic, so we don't want to step on any toes. So we had to do the multiplication by longhand using a rep. And then the way I ordered things, it all works out so that everything's normalized. But in case the mantissa grows, we detect it here and then we shift it by 1 bit, and then the carry will be set. So when we add the 2 exponents together, we get a renormalized number that we can then do a proper round operation on without looking for any more exceptions. And here's like a really compact little unpack routine that does the unpacking. And then down here is the round, but we don't even really need, I mean, this stuff here doesn't even really execute. So I'll see if I can maybe shave 1 instruction out of this thing somewhere. But the upper part of the code here, starting here at FP out, this is what does the, you know, the whole conversion. So it has to detect nan and 0 and then plus or minus, and then goes about messing with the floating point to try to get some, you know, the significant digits arranged so that we can print it. And this is going to clean up quite a bit, but it's just big and sloppy right now, but it's working anyway. So hopefully in the next day or 2, I'll have this ironed out, and then I'll make a new release of the tool so we'll be able to see floating point. And I don't, as you can see, it's purely scientific notation right now. Reason being, it's the simplest thing to get working at first, but I kind of like it in a way because it forces the user to always understand that they're dealing with a certain amount of precision. They have like 7.2, but I'm showing 7 significant digits plus an exponent. So it's clear that you're dealing with the floating point value and not, you know, 5 or something, which, you know, who knows where that came from. So it always shows kind of contextually what the number is. You guys have anything to say about that? Like Gavin, you think that's too austere for your students?
Yeah, I think the trick is you're competing against the Arduino, which is incredibly popular, which most of these students come in having some experience with. So we really need to make it, you know, just simple and just as easy for them in the basic stuff. And I think most of the floating point numbers they're typically be working with are just, you know, a couple hundred in terms of the integer part.
Right.
And then you maybe just, you know, 3 or 4 decimal places to the right of the decimal. So I think that's you know, mostly what they're gonna be doing. So the need for scientific notation won't be that great in most of the sorts of applications we typically do. You know, reading in a voltage is gonna be one of the most common things we do, and trying to convert that from just some number of bits into an actual voltage value at the decimal point. So, you know, on the board I'm creating, for example, we're probably going above 12 volts. So, so 12.673 is a number we'll probably see a lot, or you know, 6.273 or something, but not, you know, some crazy scientific exponent. Another thing I was thinking about that might be useful to add to the compiler in the Propeller tool is some kind of a flag that you could toggle on and off the little checkbox under preferences. Because the #1 problem I've had with the P1 without, you know, automatic casting has been people accidentally mixing and matching floating points. So basically, if somebody's using one of these floating point method or floating point operations, plus dot or something to have the compiler and the propeller tool just kind of double check and just make sure a sanity check that it's not some outrageously large number, in the hundreds of millions, if it was looked at as an integer. So just basically, if you're doing a floating point operation on two values, just to double check to make sure that those aren't just preposterously large integer. Does that make sense? Just because I think for the most part, people aren't going to be using, way at the extremes of what floating point can represent in single precision.
Right. Yeah. Okay. Well, you're saying, I didn't get exactly, but because I was thinking about the other thing you were saying too, but you're saying do some kind of sanity check on the size of the numbers they're expressing?
Yeah. So almost every time where the students would use the floating point method calls in Propeller 1, which again, we had to use a lot as engineers, there'd be, they just get confused and they just try to, use a floating point method on an integer by mistake and get some crazy number, or vice versa. They're trying to use a floating point value with an integer only operation. And, the math almost instantly blows up. But because of the way the IEEE 754 works, for example, if I bring up, the exponent is up in the upper bits, everything except for the most significant bit, which is the sign. So typically, for smaller numbers, the exponent is the 127 that's, implied to have subtracted 127.
One.
So usually it's just a couple places of the exponent. So it's usually pretty obvious if you're just dealing with kind of normal floating point values, if it's an integer or a floating point, just by kind of looking at the magnitude of the value and looked at as an integer. Does that make sense?
Yeah. I wonder though, if that would be what I got right away tripped up on, you see this code here? The first thing I accidentally did was this, right? And it doesn't make any sense. So you've got to hit everything just right. You can't do this either. Right.
Right. This won't catch everything. And there's gonna be times where this becomes annoying, but just as a safety, as it's compiling, because there's not auto casting, just to say, are you sure you really want to do this, or did you make a mistake? Because the number is going to be a couple 100 million. Does that make sense?
Yeah, but it's okay. So you're saying a compile time catch.
Yeah, just a warning flag, just to say, you might have mixed up floating points and integers, and then have it in preferences. You can toggle it on and off if it gets annoying, if you are dealing with very large numbers or very small numbers for some reason. Well,
the thing is, if they express floating point numbers, like which is a number with a decimal in it somewhere, or an E, they're going to have crazy looking 32-bit values, because those.
But that's where I think the compiler can just kind of look at that as, just a quick sanity check. So if it sees a very, very, like let's say you're only using 3 bits or something to display 7, but you really meant 7.0, that'd be a really quick check just to see if the number is treated like an integer is greater than 100 million, or is it? Does that make sense?
Yeah, so but here's my thing though. A lot of this stuff's going to occur with variable contents at runtime, and at compile time, you only have a few values being plugged in, right? That's true. But again, just the more we can check just as a quick kind of sanity check flag, the better, is kind of how I see it. I'm just trying to anticipate where problems are going to rise up a lot. And again, we're competing with systems that automatically cast, and obviously I understand we don't want to do that, but I'm trying to give us every edge to be able to say this is competitive. Yeah, I appreciate what you're saying. I'm just trying to visualize, for example, let's say someone plugs in, give me an example of what the source code would look like that should trigger a warning. I haven't completely thought this out. I'm kind of shooting from the hip right now, but I'm just thinking that this is going to be something that comes up. So I'll work out an example for you. I'm playing around with an online IEEE 754 converter, just kind of messing around. And again, usually the exponent bits are always set with most floating point numbers you're going to work with. So that's kind of a quick sign, is if the number is, if it's interpreted as powers of 2, is an integer, then that number is in the hundreds of millions. And that usually isn't something you're dealing with on a regular basis when you're dealing with integers on typical microcontroller applications. So that's just sort of a quick sanity check to just see if if the user's intent is probably to make it a floating point number, or whether or not they're
treat as
Yeah,
an integer.
like did they mean 5 or 5.0? Because those wind up being really different.
But the exponent bits are always going to be the kind of, or most likely will be the tell that says this is going to be a IEEE number.
A floating point, right?
And again, it's not always going to be infallible, but it's better than nothing. Is sort of a quick sanity check. And if you could just raise a warning flag saying, hey, this might not be what you want.
Yeah.
But whether or not they could do it during runtime with variables that are changing, I think pretty quickly they'd find out when their code doesn't work, that's one of the reasons why.
Right. Yeah. All
But
right.
I think this would be more for Jeff down the line, trying to incorporate this into the Propeller tool. And again, I'll think of some exact kind of where we could create the cutoff line, whether or not it's, 2 to the 28 or less is probably an integer or something like that.
All right.
John, do you want to unmute or I can read it? Not sure if you have microphone there. So we had a comment from John. You can see it in the chat. Forcing people to deal with one format over other is not a way to make customers happy.
So I agree. What I'm suggesting is if they use a floating point operation, so plus dot, multiply dot, something like that, then it just kind of does a quick double check to make sure that they're not doing something dumb, like trying to use that operation on an integer.
Yeah, we could certainly, I mean, we have view of like constants at compile time, but the huge pitfall is maybe variable usage.
Yeah, agreed. But
And
again,
that's
if we
like-
just at least kind of take care of constants that they might use, because that's usually, I think a lot of what they're gonna be doing is just multiplying some constant by a variable.
Yeah. All right. Hey, John, can you elaborate? You said forcing people to deal with one format over others is not a way to make customers happy.
Well, it's just going along with what Gavin was saying. If you're going to use floating point, but force especially young people to do everything in scientific notation, people are just going to walk away. There are too many other choices out there. And to say, we're going to turn you into rocket scientists and be kind of preachy in that manner is not good for business. There's already enough challenges using the Propeller in the real world. Most of the people like me that say to a client, this is the device that I'm really good at and want to use, there is sometimes real serious pushback because they've never heard of it. There's not a lot of tools. I had a special effects shop tell me recently, well, there doesn't seem to be much of a library for it, so why would I use it? I don't want to have to write libraries for everything. So, these are real world business things. The chip is done. The business now is getting a real library installed. And then when you add these features, and I'm certainly in support of the floating point, but don't cripple it and just give your competitors even more rocks to throw at you.
Yeah, so I agree. Forcing everybody to use scientific notation probably isn't optimal on this. And I think if you can always just, rather than say 10, say 10.0, as you were showing in your example, that would work. And again, I think maybe that example you just showed, Chip, is a good way to explain, to sum up kind of what I was trying to say, is that if you use that some kind of a floating point operation, was it division dot and then 1 0 10, the compiler automatically looks at 10 and says, okay, well, that's really just 4 bits, and I'd expect this to be at least using 24 bits or more as a floating point number, just to kind of quickly throw a flip. Yeah. So it would have caught that mistake and at least kind of warned you, and you just say ignore if you actually knew what you're doing, or toggle it off completely under preferences if you never want to see it again.
Yeah, you've got to construct everything properly or it just won't work right, and it'll be very confusing.
But that's not unprecedented. Other languages do that too. And I think Python has changed, but I think you used to have to do what you're doing here, where if you're going to do, say, a division for floating point, you would have to use a floating point, even if it was .0. I just opened idle to check in Python 3, and that's not the case. But if you want to do integer division in Python, now you have to do backslash, what we use as a modulus operator, and that will give you an integer division. So that supports what you're doing in that for floating point and integer, we're using different symbols.
But we've discussed this a lot, that the alternative is casting, which I think just opens up a huge can of worms for, spin 2 that at this point doesn't seem like it's worth doing or really can be done within reason.
Yeah.
So I think this is the right compromise. So Chip, yeah, congrats on getting this to this point, and I just a couple little extra, polishing features like warning flags just for the as I see it, the number one mistake people are going to use is just mixing up the different formats and having integers and floating points combined in either the integer only operations or the floating point operations. So any kind of quick kind of catches we can do is better than nothing.
All right. All right, well, I'll get this cleaned up. And so we should also do, like, if we should get rid of trailing zeros and things like this when we express numbers.
It also could be when you're expressing numbers, particularly on a debug screen, you could have, I think there should be one that just kind of automatically does the number of decimal places that make sense. But you also might be able to force it to be a certain number of decimal places and just kind of round the last digit.
All right.
All right, any more questions? I was almost sure that Enrique was going to say something, but sending some chat message.
Yes. How do you guess at that? Are you hearing me?
So do you want to say something about
Harry.
this plane? Yes.
I was comparing the results on the Windows calculator, and it loses completely precision when you subtract one, for example, 1 minus 1 elevated to minus 47 and store the results. When you show at the screen, it's 1, but when you subtract 1 from the memory representation, you got 2 point and a lot of digits elevated to a small or to a high exponent. So even the way Windows is doing calculation over 64 bits is having some problems as the difference of exponents raises to a point that the representation in memory does not more get aligned to the expected results. So every type of calculation has its limits, and the way you represented it inside the memory, even if you have extra nibbles during the calculations, you can have one underflow nibble and an overflow nibble during the calculations. But when you store the results into memory and you get them back to do another calculation, the differences, the problems of representation appears. I was doing those calculations while she was explaining to got meaning about how the limits of Windows are representing using the standard calculator that comes with the system.
Yeah,
hope-
floating point's not perfect, and it's kind of like, it's a mind bender to work with. it's not clean, because when you get into these crazy exponents, I mean, imagine 256 bits that something can start at, actually more than that. And then always considering like, well, how does this relate to some power of 10 so we can extract some digits out of it that'll make some sense. I don't know, for me, it's like really taxing to work on because it's not all obvious.
My first calculator where I learned assembler, the CompuCorp ones from the 300 and 400 series back in 97.5, they have the same problem, but they have only 55 bits of mantissa, 13 nibbles, if I remember right. 13. Yes.
Oh, they probably used decimal, binary coded decimal.
They have both options. This one was one of the things I and another guy asked during the development of the P2 because we love that the P2 also have an option to do maths in both systems because it helps a lot. Now you are suffering from that problem when you try to represent and do all that maths in floating point. Because if you had some time ago, it's only a mind bender. You can do what you are doing because it will do right, but if you had decimal maths inside the P2, it will be better for you to code that kind of problem. It will be easier, less transformations. When I was solving systems from 100 versus 100 matrices using floating point numbers, at that time, it was a mind bender to keep with the results because of those problems of representation. During the calculations, we had a underflow nibble and one overflow nibble. But as long as you store the results into the 64-bit registers of the processor and call it then back to use the results of the calculation change a little bit until we will get the meaning that we are losing those extra nibbles during that transformation was a problem because everyone look at the other face and, oh, we are doing something right. No, we are thinking right because what you do during the calculations, what you store in memory are not the same thing if you are using extra nibbles. Only that. Thank you for your attention.
All right, so we have Lachlan back. He got power back. So Lachlan, do you want to continue? And then we can have more discussion after your presentation.
Yeah, sure. It shouldn't take long, so I'll just finish off. We had a 15-minute early morning power failure here for some reason, which may or may not be related to mentioning Arduino. Yeah, let me cut back to the screen. Okay, so where we got up to, we mentioned the Arduino header. The next one is 3.3 volt sensors. If you want to connect up a 3-wire sensors using servo cables, you can just bridge this rail, which is in the middle here, can be bridged over to 3.3 volts on this side or 5 volts on the other side, and that gives you a block of 8 headers, which can be connected up. The next mode is for connecting to Digilent's PMOD modules, which are commonly used with FPGA boards. They've been around for a while. I think they're now digital and might now be owned by one of the FPGA companies, perhaps.
They're owned by National Instruments.
Oh,
last time I
yes, you're
checked.
right, Gavin. Yeah, sorry, you're correct. Yeah, National Instruments. So these are readily available and they're reasonably well priced. They also do like a dual format, like where you need more pins, where you, and so I've aligned the headers here so that you can plug in the dual versions. And although what's shown in the photo there is just a single height, I guess you call it, so a total of 8 pins, you can also use dual and line headers and get the full 16 pins out through there. Yeah, so there's quite a few, like I don't know, in amongst my collection, there's a whole heap of these little, BNC breakouts and things, RCA, for audio, and they're all quite cost effective modules, encoders, SD cards.
Go to the house.
So yeah, digital PMod modules. The other thing I was just referring to before was 5-volt servos. If you want to just link that bus bar across to the 5-volt end, then you can connect up 8 servos onto that block of headers. Then we've been using a lot of the microbus, little microbus modules. Should be a K there in microbus at the top. So they have 16 pins. Sorry, they have 12 pins which connect through to the P2. Parallax sells a board which breaks 16 pins down to those 12 pins that are required. One of the tricks that Microelectronica do themselves on these development boards is they actually share the I2C pins with the SPI, with some of the SPI pins. And so that means that you can kind of get away with using a few less pins than you need to, as long as you sort of follow their same multiplexing guidelines. But that's obviously what they bake into their own products. So what we're doing is we're taking 8 pins and driving a microbus socket. For the first 5 pins, I think everything's common with the Parallax board, and then after that, there's a way of sort of multiplexing depending on whether you want SPI or I think it's the PWM and interrupt pins which get multiplexed across. So that allows you to connect 2 microbus sockets per board. And as you can see in the photo, that's the official microbus sockets, which have got the printing on the side, which makes it kind of easy to see what the pin functions are. They're a nice socket. I think Stephen Morocco was also looking at using those, or might have been playing with those at some point too. And then the final mode is for just running stepper motor drivers, like found in 3D printers and little mini mills and just about everywhere nowadays. So because the data pins are running across the top of the header here, all we've done is we've added the second set down here, which break out to screw terminals or plug-in terminals, so that it makes it easy to connect up stepper motors to the boards. So that means, you can have any combination of these kind of things on either side. So you might have a stepper motor on one side and a microbus connector on the other side. The board's been designed, you can see the chamfer in the corner here allows you to put these on each side, so you can have them, they don't interfere with each other when you run them around the P2 eval board. So you can have, 6 or 8 of these kind of flexible socket arrangements, which you can load up however you need to. And that's pretty much it.
Thank you, Lachlan. Any questions right now? If no questions.
So Lachlan, are these boards available now, and how do we get them?
They're available in that they're sitting here. I'm going to send some across to Publison. I've got his address over in the US, and I'll send them across to him. If Parallax want to, I can send them to Parallax as well. And yeah, they'll just be sort of, probably $2 each or something small, and just sold with some flat headers, which you can solder into place. Because obviously, different people want to configure it different ways. We sort of see them as a useful board just for breaking out, as needed or when needed, when you're, one short of a particular type of socket or adapter. So,
Yeah, I think it would be great if Parallax could make these available. I think that would be a very useful addition for P2 prototyping and development.
All right, let's get it done.
Right, on the way.
Okay. No
Chip,
more
you were
com-
saying something before, but you were muted. Was it? You're on
Oh,
mute.
you're muted, yeah.
I was gonna ask you if you have any code written that runs those little tiny, were they OLED displays that fit on this thing?
Yeah, Brian has been spending a lot of time with different variants, and he can tell you some of the ins and outs of using the different ones and the subtle variations. Like they're not really, doesn't seem to be a particularly strong standard around them. So, you know, Brian was explaining to me during the week about the different pixel offsets and things you've needed to insert to get things to work. So there's always a kind of yeah, well, it does connect, but, you know, you've got to do this to get it, different displays to work. And, you know, it's sort of a bit random at the moment getting products. These displays, they vary with their pins and their chipset, and there seem to be some other conventions. So, you know, they're kind of similar, but kind of not. But yeah, Brian's got some code which he's been working on, and I think also some others in the forum have also got some code. So
Yeah, last spring I bought a bunch of these super cheap from Amazon. These are the OLED ones using I2C, and I was able to hack John McPhail's I2C driver code for Spin 2 to get this to work, just kind of bare bones, same hello world type stuff. But I think there's some SPI versions available. There's some that have 3 colors. I think Parallax carries the 3-color one. But you know, this one here is probably like $4.
yeah,
I've got a couple of displays running on my bench now. I'll just grab my camera so I can show you guys.
So, Lachlan, do you want to stop sharing the screen?
yeah, I'll stop
So-
sharing. Yeah, hang on. Oops.
I don't know how this is going to look.
So Brian, you can go ahead. I think if you speak while you're showing, it will show in the main.
Yeah, I'll just see if I can. Is the screen working? Hang on a sec. Nearly there.
Yep, we can see that now.
I don't know if you can see those working.
Yep.
I think I see it in the camera. Maybe let's stop sharing. So Brian, what was the name of these displays again?
So one of them is, the smaller one is 160 pixels by 80. I think they call it a 0.96 display. And the bigger one is 128 by 128 pixels. So they're both, as Lachlan said, they both have 8 pins on them. So you have a data, a clock, a chip select, there's a register select, a reset, and LED drive, and then just a 3.3 and ground power. There's 2 different chipsets that are available that are sort of 99% the same, same sort of register sets in them. But when the manufacturers put these together, there's certain configuration pins that they use to set screen size. And so with the driver, there's different X and Y offsets that you have to set to sort of center the screen, the memory image, I suppose, into the actual screen itself. And some of that's a little bit weird. Like the little screen, for example, has a Y offset of 26 pixels and an X offset of 1, if I remember correctly. So yeah, at the moment, this driver, which I'm hoping to sort of finish off today, supports both of these displays. So you don't have to worry about all that. That's already sorted out. But yeah, there's a lot of things where the actual pixel colors are inverted on one of the displays compared to the others. All the bits are swapped, and so you've got these different modes you've got to go into to flip them back. And but yeah, they're a nice little display. And in this modes here, I'm running, it's a PASM driver, so that I can push the pixels out quick. The idea being that you could make small gauges and things with needles and things moving, and you don't get any sort of artifacts while things are being updated. But yeah, they're a nice little display. I don't know whether the camera's doing justice there. The smaller one seems to be a bit brighter than the bigger one. And the pixels are a little bit closer together in the smaller display, the density. But yeah, so that's...
Is the resolution like 128 by 128 on that one on the right?
Yeah, that's right. Yeah.
Yeah.
So that's not a bad resolution. And I have, I did have a demo. So if you just bear with me, I'll just reset the board. It might run a demo on the smaller one. I think it's flashed in. Where are we? And I've used the P1 font to do text, and it seems to look quite nice on the display. And then I've got a few scaling operations that I don't know if you can see that, that's drawing circles on there. That's using the Cordic, which seems to work quite nice. And I've got some, it has actually got a built-in scroll function in the hardware, but it's a little bit clunky to use, and it's a little bit weird because you've got screen rotation modes. So I've done my own one where I just have my own buffer that I do my own shifting and manipulation, and then I just blast that buffer out. But yeah, the P1 font, that comes up okay. I'm not sure whether you guys are seeing it clear enough. It's not a great camera.
Yeah, it's pretty clear. We can see what's going on. Yeah.
Yeah. And it just cycles around. It's just a basic test. Yeah, that's starting again now, going around. So yeah, that's what I've been tinkering with yesterday. So yeah, the way the interface works, you define a window. Let's say you want to fill a square that's maybe 8 by 8 pixels. You send out a command to define that you want to do an 8 by 8 window, and that automatically adjusts for the columns and rows, and you give it a start column and row, and then you can just send out pixels, and it'll wrap within that window that you've just defined. So you don't have to keep starting on a new line. You know, you're just going to send out 64 pixels in an 8 by 8 format, and it will automatically wrap on from each row into each column into the new row. So if you want to fill the whole screen, for example, then you just define your top left as a 0, 0, tell it how many bits, 128 by 128, and then you can just stream out the bits. But if you want to set individual pixels, you have to define a window that's 1 by 1, and then you send out the pixel data. So it's a little bit slower if you just want to set individual random pixels.
Seems
if
like
you
it
want-
would be better just to maintain the bitmap in the P2 and then just update the whole thing.
That's what I've been doing. And it's a lot quicker, obviously. You're not sending out as much data. So, and because you've got using the hub memory as that frame buffer, you've got a lot more powerful means of doing scrolls and color swaps and this sort of thing. And it also means that you know, for example, if you're doing, which I intend to do here is do sort of like small gauges and things with moving needles, you need a sort of a background image. Let's say it's the dial with all your enumeration on it, and then you can just overlay a needle, just a filled sort of polygon on top of that, and then you get a nice smooth animation. You're not sort of getting this redraw that's a mess. So yeah, so anyhow, that's what I've been tinkering with.
Well, Ryan, thank you for sharing.
Yep.
And
Yep.
and thank you, Lachlan, for jumping back into it too. And so then we are going to end the presentation section for the live forum, and then we have next week the P2 arcade machine, and the following week the P2 EC RAM memory board from Michael. And let's get into the discussion.